Thanks everyone for coming back from lunch, and thank you for the introduction, Mr. Chairman. Thank you for inviting me to this conference where I don't need to define what a qudit is. I'm really happy we are doing this. I hope we have more of these meetings in the future. My title is very ambitious towards qudit quantum computation, but seeing the work that has been done now, I think we're probably going to have it sooner than later. Um, Barry mentioned his experiments with Andrea Morello, and I was talking to him about this. He hoped he could come, but he sends his regards to everybody. Um, Let me just check, where do I point? Okay, before I run out of time later, I want to thank all the sponsors that have funded my curiosity in the last few years. Australian Research Council, Westpac, a bank in Australia, L'Oreal Foundation for Women in Science. And in Australia, I'm part of the Center of Excellence for Engineered Quantum Systems. And the work that you'll see here is part of the program that I have for that center. I wanted to come out of this workshop having an answer to this question: when will qudit quantum computation be a thing? And what I mean by that is, when can we have a qudit quantum computer? And when will the community actually recognize that qudit quantum computation is a thing? Because I don't know if you feel the same, but when I am among my circles that are not the qudit lovers, it doesn't feel that way. And I think there is a lot to do to increase the visibility of this really active, beautiful research area. And I'm glad that I think we are going to achieve that in the future. I traveled far, so I think I earned the right to show you this slide. I come from the University of Queensland in Australia. It's in a peninsula-like area beside the Brisbane River. That's the physics building over there. And we have the longest running physics demonstration in the world. It's the pitch drop experiment. If you've ever wondered whether tar is liquid or not, it is a liquid. It's been there since 1927. See, it's not just the Solvay conference, which was important in 1927. So this experiment, you can actually video stream it if you're ever bored. There is a link. I can give it to you later if you really are interested. My group in UQ is, I got a position there in 2019. As you could see, I'm very convicted for QuDits, so we are QuDits at UQ. If you're interested in any of the work that I'm gonna talk about today, please get in touch. The work that I will present today is mostly work of Jam and the two Daniels, and I hope you find them interesting. I don't think I need to preach to us that quantum technologies is interesting. This is really just a slide to show you images that I've generated in ChatGPT. So quantum technologies for quantum computing, quantum communications, and quantum sensing. And the instruction was to make the talk a bit introductory, so I'm gonna do that because I'm a textbook participant. So I'm gonna show you what the qubit is. It's a superposition of the 0 and 1. We have a lot of physical systems where we can have qubits. In particular, for example, in this rubidium atom, we can ignore all the higher levels and just consider 2 of the states and call that our qubit, the 0 and 1. But then really nothing is stopping us from looking at the higher levels as well. And that's where we get our qudit, when we have a superposition of these many more levels. And why you use qudits? Because of many advantages, like the higher information capacity. You have, it's more robust against optimal cloning. Like if you've, of course, we know quantum cloning an unknown quantum state is impossible. But if you are happy to accept that some of the trials will fail, then you can do optimal cloning. And the fidelity of that optimal cloning is actually bounded by this equation here. So if you do optimal cloning for a qubit, you will succeed 86% or 83%. If you go to higher dimensions, that would be bounded by a half. So it's more robust. You can have higher error thresholds in QKD. So in QKD, when you have errors, doesn't matter whether it's eavesdropper or some noise in the environment, you would have to discard your run if you are above some error threshold. And that error threshold is higher for higher dimensions as well. So all these things are, better than qubits. We hear that a lot, but I'm actually interested, and maybe you are too, what can you do only with QDITs? And I think I've seen some examples in this workshop of, lattice gauge theories, for example. What can you do only with qudit entanglement? I think these are really interesting questions in making the mark for qudits in this landscape of quantum technologies. Because for sure, there are things that you can only do with qudit entanglement. This is a shameless plug for an article that I wrote with Marcus in Optics and Photonics News, where we discussed a little bit about high-dimensional entanglement. Because really, it's very interesting. I got this figure from Aspurgusik's group, where they look at the entanglement structures in superconducting qubit systems. And really, it's terra incognita for high-dimensional multi-particle qudit systems. And I hope that we can have more of those research in the future, because I think it's going to be really interesting, for pleasure. Maybe for some applications as well. I want to give you an example of what you can do only with qudit entanglement. I searched through some literature and I found this paper from 1999. It's a quantum secret sharing paper from Cleve, Gottesman, and Law. And they give a protocol which is something like this. If you have a message, you want to send it to some parties, to say that's your message. You want to send it to some parties, but it turns out that your parties cannot all be trusted. Okay, so that's called an NK threshold scheme. And in that paper, they actually prove that if you only have 2 trusted parties and you still want them to recreate the message, you can use quantum mechanics, but a 3-2 threshold scheme that uses only qubits does not exist. They actually prove that it does not exist. So to do this, you need qutrit entanglement. They actually have the GHZ as an example for this particular protocol. And I think we can find some other things like this that are equally or even more interesting. And yeah, I think that's really a good direction of research. So today, I want to talk about some efforts at the University of Queensland for, I want to say quantum computing, maybe more of the quantum information processing, really building the building blocks so that we can do quantum information processing in photons, so that we can someday, work on problems that can be solved only by using qudits, or even solving problems that are more advantageous in using qudits. We've heard a lot already about the different physical systems that we have: trapped ions, superconductors, atoms. I am an experimentalist, and I specialize on photons. And I wanna say some things about photons. So one, why is it good for quantum technology? This actually was inspired by a question from my son, like, has anyone ever asked you what is quantum? What makes something quantum? It's a really hard question. And I said to him, oh, if you need quantum physics when things are cold and they're low energy, you need quantum physics. And then, talking with colleagues in UQ, back of the envelope calculation, why is photons good for quantum technology? If you actually do the calculation for, the Boltzmann, the average number of thermal photons, it's actually almost 0 because of the really high frequencies. So to a photon, the world is really cold. It's a really cold system even at room temperature, and therefore quantum effects will manifest at room temperature. If you need only coherence, you have a really good quantum system here. We've talked a lot about quantum computing now in various physical platforms. I just want to go back to the DiVincenzo criteria. I don't answer all of them, but I think it's nice to see a qudit version of it. So there you go. That's the DiVincenzo criteria for quantum computing. And you can divide that into the generation of your qudit, into the processing of your qudit, into the measurement and detection of your qudit. And the last two are like bonus if you want to do quantum communication as well, or talk about distributed computing. The last two will actually be a bonus if you use photons, because that's the only flying qubit or the flying qudit that we know. So I work with photons. I like photons. As an experimentalist, I was saying to Crystal the other day, you choose your poison. There are some things that are really hard to do with photons, but I hope I can convince you today there are some things that are really easy with photons as well. Photons are very rich physical systems. We talk about the Hilbert space of a photon. You have there the creation and annihilation operators for the photon. We talk about modes of the electromagnetic field. So you're all familiar with the dual rail encoding. Throughout the workshop, we have been implying this dual rail encoding. I just put it there, so it's clear. It's Barry here, just to be precise. So it's precise. So I'm talking about D-rail encoding in photons. Gerard, Melbourne, and I actually wrote a very ambitious article to summarize photonic quantum computing. And there you have the quantum computing possible with photons in qubit, qudit, and CV, which is really QuDits embedded in the harmonic oscillator. So if you want to have a bit of an introduction, that article is on the archive. So as I've said, photons have a lot of properties. Some of them are naturally qudit, and in particular, I like the transverse modes, this colored figure here. So the brightness is the intensity. The color is the phase, like the actual phase at that particular point in space. So really, you're seeing here the electric field. And when I talk about transverse modes, what I really mean is you solve the wave equation, and you have families of solutions. So in this one, I show you the Laguerre-Gaussian mode family. And I can assign, there's a mode group. It's the mode, the group number, which you can think about it actually as being equivalent to what S is. So it's an E-rep as well. You can use it as your E-rep. And when I talk about a quantum state in the transverse mode, this is really what I mean. I do superpositions of these modes in my photons. And you can make as many as you like. The Hilbert space is theoretically infinite, but of course, you're always limited by what you can measure in your experiment. But you can potentially go to really high dimensions. And entanglement in this degree of freedom of the photon has been shown since the early 2000s, since Zeilinger and co-workers realized that if you can generate a particular transverse mode, you can just reverse that setup and detect it on a single photon. Because if you have this particular shape being generated, if you reverse that, this one will just transform that back into a fundamental mode here that can then be coupled to a single mode fiber that can then be connected to a single photon detector. So you can detect the transverse mode of your single photons. And in fact, that's the exact experiment that they did in 2001 in this paper here. And a lot of the work that I've done for my PhD, a lot of the other groups as well have done, is to make this a more versatile technology. In particular, we use spatial light modulators, which makes this measurement really very programmable. Like you can really measure a lot of states. So going back to the technology, like what do we need for generation, processing, measurement, when I look at photonics, I sort of divide it into free space and the on-chip communities. For free space, the generation for single qudits is really easy. You can do it with a spatial light modulator. The entanglement comes for free in nonlinear optical processes like spontaneous parametric down conversion. The measurement we do really very well because we could use the spatial light modulator as a mode filter, and then you can connect that to a single photon detector. And with this, we've really done a lot. So this is just one example of an entropic inequality, which we have violated in our group. So it's an entropic inequality, the Winnick-Venner entropic inequality. It's a whole talk in itself, but I just want to show that we've done that up to 14 dimensions. If you go to entanglement, like violation of Bell inequality, this was done in 2011. So this one was up to 13 dimensions in Glasgow. We also did a lot of work in quantum state tomography. So this one is the problem with QuDits when you do quantum state tomography is that the scaling is really not practical. In this paper here, we showed an online quantum state tomography, meaning no post-processing necessary. We've done that with transverse modes. I've now convinced at least one group to do it in their setup as well. So Paderborn has done the same self-guided tomography in their QuDits using frequency modes. I'll just a bit of brag. So this is a log scale. So as you can see, we get really good fidelities with preparing single QuDits. We're really good at it, and we can go up to 20 dimensions. Andrew White calls this the QVigint because the Latin for 20 is viginti, apparently. So we can do up to QVigents. We can probably go higher, but the patience runs out more quickly than the experiment. So I think for free space, the missing piece is processing. So I want to show you that multiplane light conversion can be a possibility for this. And this is QDIT gates that I've done with some colleagues at UQ. So you've seen this X and Z gate already a lot of times in this workshop. For transverse modes, the scaling for the number of components is really not good. Like you're talking about hundreds of elements here if you do it this way. In our group, we use spatial light modulators for our QDIT gates. So what we have is if I say choose a 5-dimensional QDIT here, just assign modes to that QDIT. And then I have a lookup table. What does an X gate need to do? What does a DFT gate need to do? What does a Z gate need to do? And because I know the input to the output and I know optics, I can design an element, which is in this case is a phase mask, that will do those transformations. So this multiplane light conversion is really nothing but reflection and phase modulation on each of these 7 planes. And with a device like that, we are able to do these transformations on the field of the photon. The experiment setup looks like this. I mean, you can ask me questions later about it. I'll just show you pictures of it. It's really compact. These are the masks that we have. So we design that, and then we keep it fixed. If we want another gate, we design it again, and then we program it onto the spatial light modulator. And these are our results for 17 dimensions. So these are, I'm trying to alternate here the experimentally measured field and the field that we want to happen. And as you can see, there's very good agreement between the theory and the experiment. I have here some metrics. As you can see, it's still very lossy, but It's because we are using a programmable mask. You could actually increase the efficiency very much if you just have static masks that just acts like a mirror, but a more sophisticated mirror. The visibility measure is like the fidelity of that gate. So as you could see, it's really good fidelity, but we have to work on the losses. But we can go up to very high dimensions at 17D. In the last 10 minutes, I want to show some work that's not exactly qudit, but still photonic. And that's our efforts going on chip, because it will improve scalability, efficiency, it's less aligning, and it really will bring quantum photonics closer to applications. There's a review paper here if you're interested on the timeline for quantum photonics. And again, if we want to put photonic qudits on chip, there are many options: frequency, path, time bin. Again, I will focus on transverse modes, because I think for me, this is the sweet spot between having parallelism and the complexity of the chip. I think it's simpler than the frequency modes or time bin. The sources are from spontaneous processes, or you could have quantum dots as well, so that it will be deterministic. But there's a lot of work to do in the processing and the measurement part. So what I'm going to show you today are just some components that we've designed. And the message that I want to give is that it's really complicated to design for qudits on chip. This is just an example of a multiplexer for 10 modes. And you have to explore the parameter space in terms of the width, in terms of the distance of the waveguides. It becomes a bit tedious. So in our group, we are using photonic inverse design, where it's like MPLC. We design by specifying what we want to happen. And user defines input, you have the desired function, and then the rest is machine learning. And with that, we can increase the device performance. It will be more robust because we are actually putting in the fabrication constraints that we have. And this is all a package that was developed in Stanford. That's actually a figure from the Stanford group. It's called SPINS. And it leads to better and quicker designs. I'm going to skip through this slide, but I just want to show you what I mean by inverse design. So that means we have a design area. We have an objective function that we are trying to minimize. And then we take whatever the permittivity distribution is and then threshold it to get our device. So say this one. So in this one, I'm trying to design a multiplexer. So TE0 goes out this port, TE1 goes out this port. That's my cost function. We simulate it. It takes about 8 hours on our desktop. And these are the designs that we have. It looks funky and messy, but it actually works. We have fabricated these devices now, like just some metrics. We have fabricated these devices. As you can see, it's actually a lot of solutions are possible. We pick the best ones, and then we fabricate it. We check the performance. These are some of the devices that we have fabricated, and as you can see, there's really good uniformity in the performance of the devices. So that's a multiplexer. We tried designing a mode beam splitter. So this is a device which would split equally between TE0 and TE1. And we've got designs like this. Again, it works in the simulation. So once we've got these two devices, we said we're going to try a Hong-Ou-Mandel interference. Because what do you do if you have a mode beam splitter and the mode multiplexer? You do Hong-Ou-Mandel interference. And it's really like the Hong-Ou-Mandel interference that we know and love, except that it's in modes. So similar to this experiment here, which has done it for frequency modes. So we're trying to recreate this paper here, but in silicon and on a much smaller footprint. And we've got that device now. So we just put them end-to-end multiplexer, beam splitter, and multiplexer. And then we borrowed single photons from our colleagues at Griffith University because they have really good indistinguishable 1550 photons. And we put it on our Hong-Ou-Mandel on-chip device, and look at that. So that's really good mode beam splitter on chip. The red line is actually a theoretical fit. We get 99.56% visibility. We looked at other devices just to check the theory that we have for fitting the visibility. And as you could see, we have reproducibly high visibility here. Just to check our theory, we looked for the bad ones, for the badly fabricated devices to check that we can really test that we understand what the visibility is. So yeah, I'm excited about this. I think the next step would really be to extend it to higher dimensions. My 30 minutes is up. Oh, I have 5 minutes. OK, well, have time for questions then. What I wanted you to take home is that, one, photons are good for quantum experiments and quantum technologies. If you need an experiment with good preparation fidelity, with good measurement fidelity, like we can do POVM, we could do projective measurements to really high dimensions, photons are good. Not everyone's gonna simulate lattice gauge theories. Like that one we haven't figured out with photons. Maybe it's impossible, maybe not. But it really is good for some things. And that, quantum systems, they are naturally high dimensional. QuDits are ubiquitous. My poison is these transverse modes. I really like them. And the approach of designing devices by specifying what you need them to do is promising. When I first saw our inverse design chips, I was trying to, what is happening here? It's like if you're comfortable giving up some of the intuition, then you can do inverse design. And having said that, we are trying to understand the inverse design. Like, I think it's really interesting why these things work. And so I'm working with the colleagues understanding that as well. But if you just need a device that works, does what you need it to do, then it's really a promising approach. And with that, thank you. Thanks for the question time.